Good afternoon, everybody. Hope everyone's having a great session so far. And thank you for being here for this talk. I'm here to present a unique study done on solving combinatorial optimization problems by simulating quantum annealing on NEC's existing HPC hardware. And the use case that we have taken is like a supply chain optimization problem for the oil and gas and energy market in general. This innovation was done in Japan, and as part of the same team, I'm here to present the studies that were done by Deepak and Momose-san in Japan. So speaking about what the use case is. Now, efficient transport of energy is and has been one of the key necessities for the energy industry. And the requirement is to get it done at low costs. So if you look at the image here, on the left are possible sources of energy, followed by the methods of delivery, and straight up, right to the consumer. And if you look at each connection here, then and you follow it through right to the consumer, you will realize that each one of these is a possible solution to solving this delivery problem, but which one is optimal? The sheer number of combinations to solution is massive. And the challenge kicks in when you bring in real-world constraints such as delivery restrictions, schedule restrictions, product availability restrictions, and that's when this problem becomes really complicated. And in computational terms, this is known as like an NP-hard problem or a combinatorial optimization problem. So before we delve into the use case, let us take a couple of steps back and see what's understand a couple of things closer. So what is a combinatorial optimization problem? To understand that, let's break it down into combinatorial problem and then see what optimization is. So a combinatorial problem is basically, as the name suggests, something that has multiple combinations to solution. And it is characterized by an objective and the conditions to achieving that objective. So for example, I have to go from point A to point B at the least cost is the objective. And any conditions like preferred mode of transport or a preferred time of the day to travel, or let's say a flat tire could be a condition to achieving that objective. So it is basically solved by finding a group of discrete, finite set of objects that satisfy the conditions to meet the objective. And if all the conditions are not met, but the objective is achieved, it is still a candidate solution. And in case where all the given conditions are met and the objective is achieved, it is an actual solution that you're looking for. So to solve these combinatorial problems and to optimize them, there is a way to do it. So an optimization problem is prepared by using math. So the objective that we were just talking about, to represent that as a function, a mathematical function, and then to consider this as a maximizing problem or a minimizing problem to that objective function will lead to the optimization of that combinatorial problem. And to find the solution with its optimal quality. All right, so let's look at this curve and consider this as the entire solution space for the objective function that we just created in the previous slide. So every point on this curve represents a solution, but then the local optimas, they represent a minimum state where we could find a solution to it. And this kind of a solution space is typically too large for an exhaustive brute force search on all these numerous local minimas. And this condition is basically So the challenge is basically that the solution space is too large, and it is often encountered in traveling salesman problems, supply chain optimization problem, which we are discussing right now, circuit designs, protein structure predictions, etc. These are all examples of how a combinatorial problem is a complicated problem. So what do? We let physics handle this. A fundamental rule of physics is that everything tends to seek a minimum energy state. For example, hot things cool down over time, and objects, they roll off hills. So this behavior is also true to the world of quantum physics. And quantum annealing simply uses quantum physics to find low energy states of a problem, and therefore the optimal or near optimal solutions. So if you look at this solution space as the energy spectrum for a quantum system, then you will see that the optimal solution is at the lowest energy state, and we can consider this as a minimization problem. And in the current, so in this context, you can solve a combinatorial problem by using quantum annealing. Simulated annealing is basically a probabilistic meta-heuristic approach of execution of the quantum annealing, and we have used the NEC's vector hardware for this activity. So the word annealing, it comes from metallurgy, where it's a process of heating a material to critically high temperature levels, so that there are changes in the structure or the properties of that material, followed by cooling it so that it retains the change. So for example, that's how you forge swords. And simulated annealing in this context is a probabilistic meta-heuristic technique inspired from the process of annealing metals, and first we use it to solve optimization problems, as we discussed. And the goal is to achieve minimum entropy that results in high probability of success of achieving a speedy as well as accurate solution. So speed and accuracy are the two goals for us. So in the quantum world, a variable can be denoted as the state of a variable can be denoted as either true or false, like a classical bit, or also like a magnetic spin, an upward spin and a downward spin. Physically, they're both the same things. These are just denotions. So if there was a problem that had 3 spins attached to it, or 3 variables, then to solve that problem, one would require 2 to the power 3 or 8 combinations. And if you look on the right side here, you will see all possible combinations. Oops, I'm using it wrong. Yeah, you look at all the possible combinations here. And if you were to look at this in your mind as zeros and ones, then what you're really looking at here is a truth table. And in this condition, all combinations of the 3 spins have been pointed out, and the one with the lowest energy associated with it has been identified as the optimal solution. So to solve larger complicated problems, of course, we would require more than 3 spins, and the magnitude of that problem can be understood by just by increasing the 3 spins to 10, you have 1,000, 1,024. By increasing it to 20, you're already in the millions, and by 30, you're already in the billions, and you can just imagine how huge basically this the problem becomes. It explodes exponentially. But what we are talking about here is not really an exhaustive search, but we are using quantum annealing to use natural phenomenon to basically to find the lowest energy from this massive solution space. Having understood what simulated annealing is, this slide shows how NEC has innovated on the simulated annealing aspect. So let's start with this part. So in existing search or in existing annealing algorithms, we explore the curve by visiting each point, and we find these local minimas. And these represent the constraints and the parameters that we were talking about. What we are doing in the vector annealing stack at NEC is we are skipping where the constraints are basically where the constraints are not met. We are able to skip those specific parts and avoid and eliminate some parts of the objective function from the solution space itself. And basically by doing this, by finding these skips, we reduce the computational complexity, thereby getting up to 50 times acceleration by skipping wherever the constraints are being violated. So that's one innovation that we have done on the quantum annealing. And if you look at this part where you will identify that a spin matrix and the spin state is actually a matrix vector operation, and the vector engine architecture is indeed where that specializes for these kind of computations. So using the hardware's own capability, we get a 6 times further acceleration by just using the vector architecture that we have. And this stack has been assembly tuned for our hardware. So by using this simulated annealing on the vector engine, we are seeing immense speedups. And given the memory on chip, we are able to process fully connected 100,000 qubits on one vector engine card. And with multiple cards, you can support even larger number of qubits. So 100,000 times n, that's the number of cards to the power half, like square root of that. A quick review of the solution stack. So at the bottom is a typical x86 server that has a vector engine PCI card installed on it. On top of that is our vector annealing engine, which is a library. And all one needs to do is call the Python APIs. So what really is happening is you have a problem, you formulate it in terms of what's understood by the library, and then everything is just library calls, so pretty much automated. So the path, the approach from a problem to a solution using this vector annealing approach is more or less automatic. The only intervention where you have to do is to formulate the problem manually, and I'm going to touch upon these aspects. And after that, to convert the problem in terms of a QUBO model to calling the vector annealing and to obtaining results is an automatic process. So this entire thing is very simple. The learning curve is very easy. Now, having understood the basics, let us just come back to the use case, which was originally to solve a supply chain problem. And let's try and understand that using some simpler constraints and a simpler example. So what we see here is a route optimization problem, which is basically, it could be any delivery agency. The problem is basically to have cargoes delivered from a distribution center to all possible delivery locations and find the shortest path and basically save on cost. Now, that being the objective, let's see what the conditions are and what the constraints are. Now, we see that there are 15 delivery locations and 18 packages. Now, one condition is that the capacity is 18, so it has to be 3 rows of 6 packages because cargo is removed from behind and above. Now, there are 15 delivery locations, so there needs to be free space in the cargo bed, and the heavier cargoes cannot be stacked on top of the lighter ones. So let's consider these 3 simple conditions that will lead to adding constraints to our objective function. And you can see there are further details that the red ones are 5 kgs, the green ones are 15 kgs, the blue ones are 25 kgs. So that's basically, we have a combinatorial problem at hand, and we can solve it by defining or formulating the problem. So what you can see is with improved delivery efficiency, you can reduce the delivery time and the burden of the delivery staff. How we do it? So this slide actually goes a little into the nitty-gritties of how a Hamiltonian is formed, but the idea is to show that it can be done. So we consider an objective function and we call the Hamiltonian HD, which in simple words is just the distance from the distribution center. Then you add the distance between the I and the I plus 1th delivery destination and then back to the delivery center. This is the function that needs to be minimized. So shortest path, shortest distance. And then each Hamiltonian is a constraint where you can say visit a certain location. It could be twice because 18 packages and 15 locations. And another constraint is that multiple packages cannot be delivered to the same point. Then the third constraint is penalize when the heaviest luggage comes on top. And the final Hamiltonian is just added by creating these quadratic equations. So all you need to do is know your basic math so that you can convert what you need in terms of a quadratic equation. And that is all. This is the final Hamiltonian that needs to be fed. So it's fairly simple. Speaking about the results, we took this problem of 15 locations, and there's a data set that we used. And we ran this on existing annealing solutions. This graph on the left represents time of execution. And there were no special tunings done. The quadratic equations that you see in the previous slide are exactly what were fed to the Cubo formulation. And with this, we see that the time in seconds is, in these graphs, lower is better because the time to solution is on the bottom. Within 1 second, you can see that the D-Wave Neal simulated annealing and OpenGIJ on x86, they took less time, but the broken and the dotted lines show that the constraints were broken by the solver. So the objective was achieved, but all objectives were not met. And in terms of distance, again, you can see that the lowest distance is best, and with the vector annealing, the accuracy aspect is also better than the available solutions. Bringing it to the energy industry, where 15 locations is very small, we used more data sets from 51 to 200 locations. And you can see on the y-axis here, these are the number of locations from 51 to 200. And we see very similar results, that the time of execution is comparable, but since the solid lines show that all constraints have been met and the objective has been achieved. Similarly, the distance or cost in these terms is also pretty good, and all the solid lines indicate that no constraints were broken. We did further optimization by using sweeps. Now, sweeps are a parameter where you can, with more sweeps, you come closer to a more accurate solution. And as you can see, the time to solution and energy, it basically, the results are obtained using these public data sets. And just by increasing the number of sweeps, you could reach better optimized solutions. On top, you see less number of sweeps, so the speed was the target. And with large number of sweeps, the accuracy was the target. And here you can see that for all conditions, we see unique solutions and complete solutions that satisfy all constraints and meet the objective of reducing the cost in the shortest distance. So while this was some work that we are doing internally on oil and gas projects, we have some in the last year, we have some actual operations that have been deployed in Japan. There are companies in Japan that are basically using this solution. And with this, you can see that the delivery parts of engineers and dispatch, delivery of parts and dispatch of engineers has been optimized using the vector annealing solution in the real industry space. Companies are using it. You can see that the delivery time, destination, the parts, and the transportation modes, they basically, there are a huge number of combinations which have been optimized. So since last October, this is an actual operation where 120 minutes per day has been reduced to 12 minutes per day, and 30% cost reduction and CO2 reduction as well. So the personnel, they used to come early in the morning, plan the logistics for the day, but with the help of annealing, vector annealing, this is an actual product that has been purchased in Japan by a company, and they are using it in their daily operations. And we're able to achieve this in within 12 minutes. So having touched upon the use case, we have more use cases where the same problem is being solved for wind farm layout optimizations, where 10 hours of calculation time has been reduced to 10 minutes of calculation time. And you can read the press release on this link. And similarly towards advanced material informatics, where you can use AI and machine learning to create a predictive model of the impact of material type, and then further feed it to the quantum computer or the vector annealing library to find the optimal combination of the amount of material that expresses the characteristics target value. So concluding, we see that simulated annealing and specifically vector annealing can be used to solve complex real-world problems, and using multiple optimization problems. It's very easy to adopt. You just need to know Python and basic math. And NEC continues to work on solving more combinatorial problems, and like knapsack scheduling. And with all the in-house work, we are also planning to take that to the industry and make it more available to various markets. So thank you for your time.
Okay, do we have any questions?
So thanks for the talk. And another way of doing the same simulated annealing could be using a local minimizer, but just having some random energy fluctuations to your objective function, right? So basically escaping the local minima by if all the local minimas are varying within a straw. Have you explored that angle? Is it fast? How does it compare?
Well, yeah, that would be an energy minimization problem, and we are basically in this, the internals of the simulated annealing library is just basically, we have created or taken how the quantum, the way the quantum annealing works has been basically adapted inside the library, which is a different form of energy minimization. And for, I think we have not used other energy minimization techniques, but they would still be like, a classical compute as opposed to what this is.
Time for one more question.
I have a quick question. No, that's fine. Can you hear me?
I can.
That's the basic. Thank you. So earlier this morning, there was a question I asked, like, analogy between HPC and non-HPC, right? That was a good example, which we run into all the time. What would be your best analogy between HPC and the quantum in terms of accelerations and performance and speed?
Yeah, so as we discussed in the first slide, the categorization changes where the nature of the problem changes. We identify these kind of combinatorial optimization problems as NP-hard problems. So these are basically the sheer amount of combinations that you have to create. It becomes a difficult problem for a classical computer to solve. So the whole idea of quantum kicks in where the capabilities become different between the way to compute. What HPC is, it will continue to be what it has been doing great, by using simulations and machine learning, and using a lot of data to parallel process a lot of information to create simulations. But in this case, as we saw, what we are doing is not really exploring the search space using exhaustive search algorithms, which sounds like an HPC problem, but we are trying to replicate a natural phenomenon to do like an entire search of the entire solution space. So, well, the best case looking forward is that HPC and quantum, they combine forces and solve difficult problems, like one of those material informatics problem that I showed, where you're using artificial intelligence and then taking the output of that and feeding it to a quantum annealing simulator to get the best solution.
Okay, let's thank our speaker one more time.
Thank you.